Hello students, good afternoon. Let us start the ITC class. In the yesterday's class, we had worked out an exercise using the joint probability matrix, and you will have to keep recalling that particular diagram where the joint entropy, the source and destination entropies, the mutual information and equivocation is correctly depicted, and based on that particular diagram itself we can write all the expressions for the mutual information or for the equivocation or even for the joint entropy as well. So today let us see the properties of mutual information. The mutual information of a channel is non-negative, that is I of A semicolon B is always greater than or equal to 0. If it is 0, that means those two circles are not overlapping. That means there is no information from the source to the destination. And if it is greater than 0, then it is meaning that the two circles are overlapping to some extent, and then the information from the source is received at the destination. If the mutual information is equal to source entropy, then it means that the complete source information is transmitted to the destination. So naturally, the mutual information cannot be negative. As such, information cannot be negative. Next thing is, mutual information of a channel is symmetric. I of A semicolon B equals I of B semicolon A. Because basically the mutual information is nothing but the overlapped area in between the two circles. Or if I have to define it mathematically, I of A semicolon B is equal to H of A minus H of A slash B. Now it will be the same case other side, where I of A semicolon B equals H of B minus H of B slash A. That way, the mutual information of a channel is symmetric, means whether you consider from source to destination or from destination to source, the content of the mutual information is going to remain the same quantity. So that way it is symmetric. Now the mutual information can be expressed in terms of the entropy of the channel output as I of A semicolon B equals H of B minus H of B slash A. This we already know. The mutual information is related to the joint entropy of the channel as I of A semicolon B equals H of A plus H of B minus H of A comma B. Sum of the source information and the destination information, and subtract the joint entropy from this sum, that is going to be the mutual information. This also we know. Now there is a summary of all the formulae. You are already familiar with all these formulae. Again it is shown here so that you can remember it very well. So H of A slash B, the equivocation, is H of A minus I of A semicolon B. Same way H of A slash B equals H of A comma B minus H of B. Joint entropy minus H of B is H of A slash B. Always visualize that diagram, you will get this equation. Similarly, H of B slash A equals H of B minus I of A semicolon B, or H of B slash A equals H of A comma B minus H of A. I of A semicolon B equals H of A minus H of A slash B. It is also equal to H of B minus H of B slash A. It is also equal to H of A plus H of B minus H of A comma B. All these equations we have already seen. Let us proceed further with this particular module. The rate of information transmission. We had worked out some exercises on this in the first module itself. Now it is slightly being revised here with the context of mutual information. The average rate at which information is going into the channel is given by R equals H of A into RS bits per second. What is this RS? RS is the symbol rate at the source. So symbol rate into H of A equals R. That is how we used to find out the information rate in the beginning. But now we know the complete h of A is not going to be transferred to the destination. As channel is non-ideal, complete source entropy will not reach the destination. So, but due to impairment in the channel, the actual information received will be lesser. In fact, with respect to the receiver, it is only the mutual information that corresponds to the actual information that was transmitted. We are already familiar with this concept. So now, dt equals I of A semicolon B into Rs now. We will have to redefine the data rate of transmission as the mutual information into Rs, because as far as the destination is concerned, it is only the mutual information that contains the source information into the symbol rate, or dt equals h of A minus h of A slash B into Rs bits per second. Here Rs is referred as symbol rate or bit rate or data rate, whereas dt is referred as the transmitted information rate. Please remember these things. Let me annotate. Now the data rate is different and the transmitted information rate is different. We can also call this data rate as symbol rate and as bit rate, but the transmitted information rate is different. Okay. Fine. The rate of emission of symbols from the source, or if it is in terms of bits, then it is the bit rate, or that itself we call it as data, then it is called as data rate. All these are bits per second. But here dt is in terms of the mutual information. So dt refers to the transmitted information rate, means even though the source is emitting those many symbols or bits, the amount of information received at the destination is going to be lesser. Just a minute, I will have to put a signature here. Okay, to continue with the class, the source may be emitting 100 megabits per second, but out of that 100 megabits per second, how much megabits per second information is going to be received at the destination? That depends on the mutual information. So, let us say this Rs is 100 megabits per second, whereas this mutual information is, let us say, sorry, I should say not RSS 100 megabits per second. Earlier we had this symbol rate along with the entropy there. We had h of A into RFS. That h of A is replaced by I of A semicolon B. So let us say together along with the h of A into RS, it was 100 megabits per second at the source. Now I of A semicolon B will be definitely less than h of A. So dt, if you get 90 Mbps, then you should say it's a very good communication channel, only 10% error. If dt is 80 Mbps, 70 Mbps, 60 Mbps, even if it is 50 Mbps also sometimes, if the channel is introducing a lot of noise, then you may get only 50% of the information that was transmitted from the source. So this way, you can understand now why the term equivocation is important here. We know the source entropy, and if we know the equivocation, then we can find out the mutual information, and then we can actually find out the transmitted information rate. That way we can characterize our communication system in terms of its efficiency or whatever. Let us have an exercise now. For the symmetric binary channel, what is the meaning of the symmetric binary channel? We had discussed this symmetric binary channel earlier, where if P00 equals P11, then that is called as symmetric binary channel. Means when 0 is transmitted and if 0 is received, if that probability is equal to 1 being transmitted and 1 being received, then that is called as symmetric binary channel. Now you can see here, this is also P and this is also P. P00 is also defined as P, P11 is also defined as P here, small p. And naturally we have P01 is 1 minus P, P10 is also 1 minus P now. Now this is a symmetric binary channel. Otherwise, in an asymmetric binary channel, this P00 may not be equivalent to P11. What is a binary channel? Binary channel is the one which is going to have only two symbols being transmitted through it. So that is the definition of symmetric binary channel, where we have this P given as 0.9, small p given as 0.9, and he asks to find the rate of information transmission, that is dt. Earlier we had this capital R. Capital R was defined as h of s into rs. Now this is a dt is nothing but I of a semicolon b into rs. So find the rate of information transmission with p equals 0.9, assuming the symbol rate as 2000 per second. So rs is given 2000 per second, and P00 equal to P11 is given 0.9. Using this data, we can write the channel matrix or the noise matrix. Now the probability of each symbol is given. Probability of 0 being transmitted is 0.6 and the probability of 1 being transmitted is 0.4. This is the source symbol probabilities. Now using the source symbol probabilities and the conditional probabilities given here as 0.9. So using the source symbol probabilities and the conditional probabilities, we can write the joint probability matrix. From the joint probability matrix, we can find out h of x, h of y, we can find out I of a semicolon b, and then we can find out the information transmission rate. Let us solve this exercise now. Given P of x1 equals 0.6, P of x2 equals 0.4, that is given. The probability of 0 is 0.6, probability of 1 is 0.4 from the source, that is given. Now the channel matrix can be written because that P is given as 0.9. Capital P of y slash x equals P 1 minus P, 1 minus P, P, because this is a binary symmetric channel. So it is 0.9, 0.1, 0.1 and 0.9. Now JPM can be written as 0.9 into 0.6, then 0.1 into 0.6, then 0.1 into 0.4 and 0.9 into 0.4, because the upper row corresponds to x1 and the lower row corresponds to x2. In other words, the upper row corresponds to the symbol 0 and the lower row corresponds to the symbol 1. That way, 0.9 into 0.6 is 0.54, 0.1 into 0.6 is 0.06, 0.1 into 0.6 is, 0.1 into 0.4 is 0.04, 0.9 into 0.4 is 0.36. Now this is P of x comma y. This is the joint probability matrix. From this matrix, we can find out now h of x and h of y. Why? How? Through the rows, through the columns. Now the row will give you the probability of x1, x2. Column will give the probability of y1, y2. But the row we already know, it is given. You can also find out 0.54 plus 0.06 is 0.6. 0.04 plus 0.36 is 0.4. But that is already known to us. So h of x is 0.6 into Lg of 1 over 0.6 plus 0.4 into Lg of 1 over 0.4. We get 0.971 bits per symbol. Now P of y1 is, add the first column elements of JPM, 0.54 plus 0.04 is 0.58. Now find out for P of y2, 0.06 plus 0.36 is 0.42. Now therefore, h of y is 0.58 Lg of 1 over 0.58 plus 0.42 Lg of 1 over 0.42 is 0.9816 bits per symbol. You can see h of x is 0.971 bits per symbol. H of y is larger, 0.9816 bits per symbol, which simply means there is noise there at the receiver. Now h of x comma y is what? The joint entropy is the entropy of the complete JPM. Entropy of the complete JPM, that is 1.4402 bits per symbol. Now we have the joint entropy, we have the source entropy, we have the destination entropy. We can find out the equivocation. So now the mutual information is given directly. We need not find out the equivocation as well because we know this expression. I of x comma y, x semicolon y equals h of x plus h of y minus h of x comma y, that we get as 0.5124 bits per symbol. That means out of 0.97 bits per symbol information that is transmitted, only 0.5124 bits per symbol is actually received at the destination. Remaining is noise. So now dt, the transmitted information rate, is given by dt equals 0.5124 into 2000. The source symbol rate is given 2000 or 2 kbps. So, but the mutual information rate is only 0.5124. So we get 1024 bits per second. That is the effective transmitted information rate. Hardly 50% because this mutual information itself is around 0.5. That means out of the complete information that is transmitted at the source, about 50% of the information is received at the destination. Now if you have understood this, the emitted information rate is R equals 0.971 into 2000. What is this 0.97? That is the source symbol. Let me admit the student. That is the source symbol. See here, h of x is 0.971. Source, not source symbol, source entropy. So, the emitted information rate is 0.971 into 2000, that is 1942 bits per second. So, out of 1942 bits per second, only 1024 bits per second is the actual transmitted information rate. So the lost information is 1942 minus 1024 is around 918 bits per second. That is actually lost. Now can you do this exercise? Can you do this exercise? Repeat the same exercise for p equals 0.5, p of x1 equals 0.7 and p of x2 equals 0.3. Now to help you, I am already showing the channel matrix and the joint probability matrix. See, p is 0.5, so 1 minus p is 0.5, 0.5, 0.5. Now 0.5 into 0.7, here the probability given is 0.7 and 0.3. 0.5 into 0.7 is 0.35. Again 0.5 into 0.7 is 0.35. This 0.5 into 0.3 is 0.15. 0.5 into 0.3 is 0.15. Now can you find out h of x, h of y? Can you find out h of x comma y? Can you find out dt on your own? I'll give you some time. I expect at least some of you will tell me the answer now for this exercise, which is the same as the earlier exercise, but only the values are changed. I'll give you 3 minutes time. Quickly give me the answer. Put your answer in the chat box. I'll wait until then. There are 22 students. Let me see who will work out this and who will tell me the answer. Okay. Kuldeep has given me the answer, mutual information is 0. That is right. Yes, Indrajit has also given the answer, I of A semicolon B is 0. That is right. And Chandramohan and Harshita have given the h of x value 0.8812, 0.87. That 0.87 is slightly wrong. You will have to verify. H of y is 1 bit per symbol is what Manideep is telling. H of x is 0.8813. That is correct. So mutual information is 0. That is right. Let us see the actual answer. By the way, now you have found out that the mutual information is 0. Can anybody tell why that mutual information became 0? Let us see the value of the R later on. But can anyone tell why the mutual information became 0? When mutual information became 0, that means that none of the source symbol reached the destination. So can you find out just by looking at this exercise, just by the observation of the values, can you tell me how come mutual information became 0? Can anybody put the answer? y1 slash x1 equals y1 slash x2 is what Indrajit has told. Value of p and 1 minus p are same. That is what Harshita has told. Correct. What does it mean? It means that the signal and its noise are having the same value. Now p is 0.5, 1 minus p is also 0.5. You can look at this. Now this is p, probability of 0 being transmitted, 0 being received. Now this is the probability of 0 being transmitted, 1 being received. Now probability of 0 being transmitted and 1 being received is noise actually. But probability of 0 being transmitted, 0 being received is signal actually. Now the signal to noise ratio is 0.5 by 0.5 is 1 itself. Any system which is having a signal to noise ratio as 1, that means what? Noise and signal are equal in amplitude. In such a case, how can we rely on this communication system which is having a SNR equal to 1? So for that reason itself, in this exercise, we get mutual information equals 1. Just a minute. Okay, so let me show you the solution now. Now from this JPM, we can find out h of y is 2 into 0.5 Lg of 1 over 0.5, that is 1 bits per symbol. This is nothing but 0.35 plus 0.15 is 0.5. Again 0.35 0.15 is 0.5. So 2 into 0.5 Lg of 1 over 0.5 is 1 bits per symbol. H of x is, it is given p of x1 as 0.7, p of x2 is 0.3. So h of x is 0.7 Lg of 1 over 0.7 plus 0.3 Lg of 1 over 0.3 is 0.881 bits per symbol. Now h of x comma y is the information content which is there in the JPM. So 2 into 0.35 Lg of 1 over 0.35 plus 2 into 0.15 Lg of 1 over 0.15 directly from the JPM. Now what is I of x semicolon y? H of x plus h of y minus h of x comma y. Now here it is 1, here it is 0.881, 1.881 minus 1.881, that is going to be 0. So mutual information content is 0. In this case, R is 0.881 into 2000 symbol rate. So 1762 bits per second or 1.72 bits per second. Even though the source transmitted 1.762 kbps, the receiver did not receive any relevant information, which means h of y is a total garbage. Whatever is this h of y, that 1 bit per symbol is a total garbage. Why this happened? This happened because SNR equals 1 here. That means P of y1 slash x1 and P of y1 slash x2 are equal. When they are equal, the signal to noise ratio is unity. When it is unity, that is how we got mutual information as 0. Let us proceed to the next topic called channel capacity. We had discussed this channel capacity even in the first module slightly differently with respect to the entropy. There also we had considered the signal to noise ratio. Now let us discuss the channel capacity in terms of the mutual information. The mutual information consists of entropy of the source and the equivocation, in which the entropy of the source is independent of the channel. The entropy of the source is independent of the channel. Therefore, the information transmission can be maximum when the mutual information attains the maximum value, which is h of a. Now, the mutual information when is equivalent to source entropy, then there can be maximum information transmission. This we have already seen. But as this is an ideal case, we can state that the channel capacity of a discrete memoryless channel is equal to the maximum average mutual information in any single use of the channel. That means, if at all we measure the mutual information in terms of transmission over a period of time, then we can write this capital C equals maximum of I of A semicolon B with respect to P of A. That means probability of the source symbols into RS is the symbol read from the source. So this channel capacity is measured in bits per channel use. That means the capacity of this channel, we cannot say exactly it is these many kbps. It may vary over a period of time. So wherever we get this maximum mutual information, we have to multiply by the source symbol, and we can say this is the number of bits per channel use. We have seen that channel capacity is 0 for a binary symmetric channel when P equals 0.5. In the exercise which we right now worked out, we have seen this. Conversely, C will be maximum when the transition probability 1 minus P is 0. That means we will have P00 and P11, they must be equal to 1. And P01 and P10, they must be equal to 0. Then we can say we transmitted 0, we received 0. We transmitted 1, we received 1. In such a case, the transition probability 1 minus P must be 0. Then C will be maximum. So, when 1 minus P is 0, we can plot a curve with respect to this P or 1 minus P and C. When we plot such curve, the following curve illustrates the channel capacity plot with 1 bit per channel use. Considering 1 bit per channel use, this is the curve. You can see here in the curve, we have plotted x-axis 1 minus P, y-axis is channel capacity. Now what is channel capacity? Maximum mutual information into RS. Now, whenever 1 minus P is 0, that is when the channel capacity is maximum. We have indicated it as 1 bit per channel use. That means we are transmitting 1 bit, we are receiving that particular bit at the receiver. So when 1 minus P is 0, C is maximum 1, and C will become 0 when that 1 minus P is 0.5, that we have seen here. So between 0 to 0.5, when that 1 minus P is there, when 1 minus P is increasing, gradually C is reducing. And when 1 minus P is 0, C is having a maximum value. So you can see it this way, it is slightly a non-linear curve. It is not a linear curve as such, it is a slightly non-linear curve, because basically noise is also non-linear that way. So you remember this particular curve. We will come to a channel coding theorem now. This is one of the remarkable outcomes of Shannon's work. This is called as Shannon's second theorem. We have already seen the Shannon's first theorem, or it is also called as source coding theorem, in the previous module. In the third module now, we are seeing the Shannon's second theorem. It is called as channel coding theorem, because here we are discussing the channel coding. While we were discussing source coding, we had not bothered much about the channel or the noise. Now we have seen the effects of noise in the channel, and now the Shannon's second theorem or channel coding theorem states that if the information rate R is less than or equal to the channel capacity, then there exists a channel coding scheme such that the information from the source can be transmitted over the channel with an arbitrarily small probability of error. Let me annotate. If R is less than or equal to the channel capacity, let me write it here. R is less than or equal to C. What does it mean? The number of symbols emitted per second from the source must be less than or equal to the channel capacity. Now the channel capacity is nothing but maximum mutual information into small rs. What is capital R? Capital R is h of A into small rs. Capital R is source entropy into source entropy into symbols per second. Whereas channel capacity is mutual information into symbols per second. Now Shannon says R must be less than or equal to C, then also error can happen in the channel. Then also errors can happen in the channel, because channel will be noisy always. But if R is less than or equal to C, then a channel coding scheme can exist. There exists a channel coding scheme. What is channel coding scheme? We are introducing additional bits into the source information such that these bits will be utilized at the destination for detecting the error and correcting the error. We are going to have this channel coding scheme in the next module, in the fourth module, where we will be working out very interesting exercises. So Shannon says, if R is less than C, then also errors will occur, but the errors can be corrected by means of introducing additional bits. So there exists a channel coding scheme such that the information from the source can be transmitted over the channel with an arbitrarily small probability of error. In such a case also, error will happen, error is bound to happen in the communication channel. There is no ideal communication channel at all. But in spite of the error, it is possible to decode at the destination, and it is possible to extract the information at the destination, provided R is less than C. If R is greater than C, then even if we have a channel coding scheme, we may not be able to extract that much of information. Let me try to tell you some real life example. R must be less than C. The information rate must be less than the channel capacity. For example, in Bengaluru city, people keep on traveling in the BMTC buses and in the metro trains. Now this BMTC bus is a channel, metro train is a channel. Imagine that way. Imagine that way for the time being. Now the capacity of the bus is, let us say, 50 plus 2 passengers. 50 passengers plus driver and conductor. Theoretically. But in the rush hours, not during this pandemic period now. Now all the buses are going empty almost. But in the rush hours, when there are peak hours, especially morning 9 o'clock to 10 o'clock, evening 5 o'clock to 6 o'clock to 7 o'clock sometimes, evening up to 5 to 8 also is a peak hour period in Bengaluru. Morning 8 to 10 we can say is a peak hour. Now during these peak hours or rush hours, many people will get into the same bus. Actually the channel capacity is lesser, but the information which is put into that is more. Now in such a case, how can there be effective transmission? The bus is designed for 50 plus 2 passengers and the bus is crowded with, let us say, 100 plus passengers, where some passengers will be hanging on the door and all other passengers are packed inside. Wherever one person is able to stand, there 2 people are standing. If they are jam packed there, do we expect that the bus will travel in a speed of 60 km per hour or at least 50 km per hour or at least 40 km per hour or at least 30 km per hour or what may be the speed of the bus now? It will be hardly 20 km per hour. That is one real example. One more example is, I gave you already the metro train. Now let me give you one more example. Visualize the road as the channel. Visualize the vehicles as the information symbols. Now any road is designed for a particular traffic per hour. The road quality is actually decided based on the traffic there. For example, there are some highways, 6-lane highways, 8-lane highways. Many times the road construction authority or the government itself later on will be appointing some people for audit, where they will actually measure by means of their survey. They will actually measure the number of vehicles that are traveling on that road per hour. Again, in that particular 1 hour of sample being taken, they will measure what is the heavy traffic, what is the light traffic. Cars and two-wheelers can be light traffic, whereas buses and trucks can be heavy traffic. Now the road has to handle heavy traffic also, less traffic also. Now they will have to plan the road, either the width of the road or the strength of the road or the number of lanes in the road, based on the number of vehicles that are going there. That the number of vehicles going there is small rs now. Number of symbols being emitted from the source. Now road itself is the channel. Now imagine the road capacity is, let us say, 100 vehicles, sorry, not 100. Maybe, I don't know, I'll have to make a guess, wild guess. Let me not tell it for minutes. Sorry, let me not tell it for hours. Let me tell it for a minute. Imagine in a minute, the road is designed for 10 vehicles per minute. 10 vehicles per minute, let us say that way. 10 vehicles per minute means it is 600 vehicles per hour. Imagine that way. The road is designed by means of a specific strong material, and the road is widened only to handle this much of traffic. Now let us say suddenly there is a increase in traffic due to some reason. What will happen? What will happen is the road will not be able to handle that much of traffic, and there will be jam, there will be accidents. When Tumkuru Siddhaganga Mutt's Shivkumara Swamiji left his body, the complete Tumkur town was jam-packed, and the normal traffic between Tumkur to Bengaluru was a standstill. because from Tumkur to Bengaluru, people could not use that inner road at all. It was completely jam-packed because on that particular day, people from all over the state and all over the country came to pay respects to the Siddhaganga Swamiji, Sri Shivkumar Swamiji. So that is an event which is actually normally unpredicted. But such event which happens once in a year or once in few years, that we will have to bear, we will have to tolerate. But otherwise, can there be regular jam in that road daily? If that happens, means we know that the R is greater than C then. The information rate is greater than the capacity. Now relate this with information theory. Shannon has given us a very beautiful idea here. Shannon says, as long as R is less than C, we can always recover the information at the destination. That is what Shannon says. If the symbols emitted along with the entropy is less than or equal to the total channel capacity, then even if the errors occur in the channel, still the information can be recovered at the destination. But if R is greater than C, then we may not have an effective transmission at all. That is the concrete idea given by Claude Shannon. Now, based on this theorem, our complete fourth module is built. Means, we will have to have this particular condition met. Source should not emit more symbols which is larger than the channel capacity. There should not be more vehicles on the road which the road cannot handle. Similarly, in a movie theater, the entrance or the exit of the movie theater, it has to handle these many people per minute as entrance or exit. If that is not there, then that may not handle when people come for the movie, where when they go out after the movie is over,